My name is Barela, and my mentor's name is Professor Garcia Cervera from the Mathematics Department. The title of my presentation today is Multi-Resolution Algorithms for Sparse Matrix Representation. So what is it all about? My research involves taking a large-scale dense matrix, which is a matrix populated primarily by non-zero entries, and transforming it into a large-scale sparse matrix, which is a matrix populated primarily by zero entries. The multi-resolution algorithms that I'm working with first require that we compress the matrix and then get it in a form such that we're able to compute matrix multiplication in the standard way, fast and efficient. So it's important in the form that we get data compression in terms of efficiency, and we get faster solutions in terms of the matrix vector multiplication. This multi-resolution process is widely applied to the sciences, things like numerical analysis, but also to sciences like chemistry, physics, biology. A lot of problems in these sciences reduce down to solving large systems of equations or require that we compute matrix vector multiplication, and doing this with a large-scale matrix can be very time-consuming. Also, to image processing, the data compression techniques that I'm working with are widely applied to pictures in the form of compressing them for memory storage. This is just a quick three-dimensional picture that's also produced by matrix vector multiplication, and it's produced in a way such that we have the multi-resolution process starting from a coarse resolution and then working our way up to the actual picture. So sort of research project goals. First we asked some questions about, well, what algorithms actually take a dense matrix and transform it into a sparse matrix? Well, I'm working with one in particular. It's called the multi-resolution process. And once we get this sparse matrix representation, we want to know, does it accurately model the original matrix to within some degree of error? If it doesn't, then the solutions it yields will not be very beneficial to us. This is a sparse matrix representation here, pictured as a spy graph. A spy graph pretty much plots all the non-zero entries of the matrix in color. So this particular matrix had over 65,000 entries, and among them 10,000 are non-zero. That's the ones plotted in the blue. So project goals, first was to ultimately learn the algorithms. Once I was able to really learn the algorithms, I can modify the algorithms. The process that I'm working with allows me to choose the sort of interpolation that we use to sort of break down this matrix and then reconstruct this matrix. So once we learn the algorithms, we can modify the type of interpolation used, and then we can run large-scale simulations to test and determine how efficient our algorithms are in terms of how sparse they get the matrix and how fast we can compute matrix multiplication. And not only that, how accurate the multiplication is as well. These are two three-dimensional mesh graphs that give you an idea of how the values look in some of the numerical examples that I'm using. And these were two matrices that I chose to use because they're pictured in a paper that I'm following, so I can compare my results to that of the authors. If you just lay the matrix down on a two-dimensional plane and let the values of the matrix be the z-axis, this is something what you get. So the matrices that we're using are somewhat smooth in one case, and then a little bit more jagged in some places, in other places. So first I'd like to talk about the experimental methods for the multi-resolution process. If we consider that we have 2 to the n data points, maybe something like we have here on the bottom where we have 16, and let's say these points represent the column of a matrix or the row of a matrix. If we just sort of delete all the odd data points from this resolution to this next resolution, and then we sort of construct a polynomial between even data points that lie around an odd data point, look at the difference between the polynomial here and the actual odd data point, we'll have a lot of values that are small in absolute value. So we repeat this process, one resolution, the next resolution, next resolution, and each one of these resolutions, we're storing the differences. So we get a new representation of our data points that consists of a lot of values that are small in absolute value. We can set a threshold, and anything below that threshold we can truncate to 0, and that's how we achieve data compression. So this is just one-dimensional data on our some experiments that we used. I chose to show you guys these 3 functions, and I want to focus on this one in particular. It's just a function represented with 1,024 points originally. We ran our data compression techniques on this, and we were able to represent it with just over 400 to within 0.001 degree of error, but also with only 40 points to within 0.1 degree of error. So to be able to take something that has 1,024 points and represent it with only 40 points to within 0.1 degree of error is pretty good data compression. And once we have this compressed form down here, we can run an inverse algorithm on it to reconstruct the data. And that's sort of what you see in this next picture, is the actual function plotted in dark blue, and then the reconstruction of each of these at various truncation levels. And you see, for the most part, it's a pretty good representation, except when you zoom in, and that's when you start to see errors here. And just note the one in teal, there's some pretty big errors, but to be able to represent this whole function with only 40 points is pretty good. So now that you have this idea for the one-dimensional scale, you can just apply it to the rows or the columns of the matrix, and you can achieve a compressed form of a matrix, i.e. a sparse form. So the whole idea of my research is not only to get a sparse matrix representation, but to get a sparse matrix representation that allows us to compute matrix vector multiplication in the standard way. And the whole idea is that if we have an n by n matrix A and an n by 1 vector F, well, we want to compute AF. And we do that as follows. We start with the original matrix representation. We can run our data compression techniques on this matrix and end up getting the multi-resolution form. That's just by applying that data compression technique on the columns of the matrix. And from the multi-resolution form AMR, we can run a reconstruction scheme on the rows of the matrix. That'll sort of reorder it, and it's what you see here. It's called the finger shape. If you just sort of throw your fingers like this, it'll have that sort of shape to it. So we go from A to AMR to AS. We call AS the standard form. Once we have that, we can compute our multiplication, and we do that as follows. We can do the multiplication AS times our multi-resolution form of our vector, and that product gives us the multi-resolution form of A times F. And then from there, we can actually get the actual product. This seems like a large process, but it can all be done in one simple algorithm. It can be done really quickly. In fact, all my simulations, large-scale simulations, were ran with 70, 80,000 entries, and it's done in a second or two, so it's pretty instantaneous. So this is just showing you the standard form on a certain matrix. Had over 65,000 non-zero entries, and then we look at the standard form for various truncations, 10 to the minus 4 and 10 to the minus 7, for different interpolation methods. And we can actually go from about 65,000 non-zero entries to 30,000, 20,000, a little less than 20,000. Just want to note real quick that the author that I'm following used a 6-point linear interpolation, and actually some of our interpolation methods, 4-point, 3-point, and 2-point, got better results in terms of a larger tolerance. So he had about 20,000, we had less and less. So that was pretty promising. Well, once we have this standard form, we actually want to do this multiplication, and we want to figure out if it's actually accurate. Well, it turns out in most cases it is pretty accurate. This is actually the multiplication of that matrix that we saw earlier times the test vector defined this way, and the product we get is this, graphed as a solution, the actual multiplication and our reconstructed multiplication, and you can't see the difference at all until you actually zoom in. And it turns out that the errors in this particular case, with a 10 to the minus 3 threshold, we had a 10 to the minus 2 error. So that was pretty good, and the error was plotted like this. And the cool thing is we saw our error turn out to be like this in a lot of cases, to where most of the error came at the beginning and the end. So some sort of results. We achieved most of the goals we came out to do. And one was to get a sparse matrix representation. We did that with AMR, the multi-resolution form. And not only that, to get a representation that allows us to do multiplication, we got that in AS. We also found that the order of interpolation we use, whether it's a third order, fourth order, fifth order, sixth order, we found that the order of interpolation used affected the sparsity of the matrix. The whole idea is that the more sparse you get the matrix, the faster you can compute the multiplication. So we want to get it as sparse as possible. Also want to note that we achieved similar results to that of Shalom, which is the author of the paper I was using. And he used a 6-point interpolation, and almost in every case we got better results than that author, except when it came to a really, really small threshold. And also future plans, we want to test the efficiency of the multiplication in terms of how fast it's actually computed. We already found that it's accurate and that it's somewhat quick, but we want to see how quick it is. And the whole idea is that it's quicker than the normal multiplication. And then we want to use these multi-resolution algorithms to solve problems that come up in mathematics, physics, chemistry, things like that. Acknowledgements, just want to thank my mentor, Professor Garcia Cervera from the math department, who wasn't able to make it